When you think of an acid, you probably picture something sour, right? Maybe a lemon or maybe something bubbling away in a chemistry lab. But what is an acid, really? Well, it turns out chemistry has not one, not two, but three different ways of looking at that question. So let's dive in and see how our understanding has changed over time. You might have learned a simple definition back in high school, but that definition, well, it starts to fall apart pretty quickly when we look at some really common chemicals. We're going to go on a little journey here through more than a century of chemical thought to uncover the different faces of acids and bases. And what you'll see is a much more elegant and, honestly, a much more powerful picture of how chemistry actually works.
All right, so our journey starts with that simple picture we all learned first. Acids are sour and bases are slippery. This was the first major scientific theory to try and pin this down. And you know what? For a lot of things, it works just fine.
So back in 1883, a guy named Svante Arrhenius came up with this really beautiful, simple idea. He said, look, when you dissolve an acid, like hydrochloric acid, HCl, in water, it releases hydrogen ions, that's H+. And when you dissolve a base, like sodium hydroxide, NaOH, it releases hydroxide ions, OH-. This theory is great because it totally explains why acids and bases neutralize each other. The H+ and the OH- just grab onto each other to form water. Simple, clean, effective. But there's a catch.
Yeah, it's a really great start, but the Arrhenius theory has a major blind spot. You see, it can only classify stuff that already has H+ or OH- in its formula and is dissolved in water. And that leads us to a classic puzzle. Let's talk about household ammonia. The formula is NH3. It's definitely a base. We all know it feels slippery and it reacts with acids. But just look at that formula, NH3. There's no oxygen in there at all, and there's definitely no OH group to just pop off into the water. So how on earth can it be a base? The Arrhenius theory it can't explain it. We need a better model. So to solve this whole ammonia puzzle, we need a new way of thinking. And in the 1920s, two chemists, Brønsted and Lowry, they gave us one. They decided the key wasn't about what a substance produces, but what it does. This new perspective completely shifts the focus. Forget about just producing hydroxide. A Brønsted-Lowry acid is simply anything that gives away a proton. And a proton is just that little H+ ion. And a base? Well, a base is anything that takes that proton. The whole reaction is just a simple transfer. Someone donates and someone accepts. It's like a game of catch with a proton. And this new definition perfectly solves our ammonia problem. So when ammonia gets into water, the water molecule itself actually plays the part of the acid. It donates one of its protons to the ammonia molecule. The ammonia grabs it, acting as the base. And what's the result? You get an ammonium ion, NH4+, and what's left behind from the water molecule is a hydroxide ion, OH-. And there it is. The reaction itself creates the hydroxide that makes the solution basic. Problem solved. Now, this whole proton transfer idea gives us this really powerful way to think about how strong an acid is. Imagine that a proton attached to an acid molecule has potential energy, kind of like a ball being held up high. An acid-base reaction is really just that proton falling from its high-energy spot on the acid to a lower-energy spot on the base. This energy metaphor is a fantastic way to picture the difference between strong and weak acids. So in a strong acid, like HCl, that proton is way up high on a metaphorical shelf. It really wants to fall, so it transfers completely, 100% of the time, to water. But in a weak acid, like the acetic acid in vinegar, that proton is on a much lower shelf. It needs a little energy boost from random molecules bumping into it to make the jump to water. And that's exactly why only a tiny fraction of weak acid molecules ever actually get around to donating their proton. Okay, so the Brønsted-Lowry theory is incredibly useful. I mean, for a ton of chemistry, it's the perfect tool for the job. But what happens when you have a reaction that looks and smells like an acid-base reaction, but there are no protons involved at all? Not a single one? Just look at this reaction. You've got boron trifluoride, BF3, reacting with the fluoride ion. There are no H+ ions anywhere to be found. No protons are being donated, none are being accepted. And yet, chemists knew this was fundamentally an acid-base kind of reaction. So our Brønsted-Lowry model, as good as it is, just can't help us here. We need to go one level deeper. And this brings us to our final and most complete picture, which was proposed by the chemist G.N. Lewis. He had this profound insight. He realized the story wasn't really about protons at all. It was about what the protons were trying to get, which is electrons. This insight completely reframes the entire definition.
A Lewis base is a substance that can donate a pair of electrons to form a brand new bond. And a Lewis acid? That's any substance that can accept that pair of electrons. It's a beautiful, broad definition that honestly changes everything. So now, let's go back and solve our protonless puzzle. The boron atom sitting in the middle of BF3 is what we call electron deficient. It's looking for electrons. That makes it a perfect Lewis acid. Meanwhile, that fluoride ion has extra pairs of electrons it's more than willing to share, making it a Lewis base. So the fluoride donates a pair, the boron accepts it, and boom, they form a new bond. And just like that, the puzzle is solved. This really shows you the true power of the Lewis theory. Okay, so we've got 3 theories: Arrhenius, Brønsted-Lowry, and Lewis. Are they all competing with each other? Which one is the right one? Well, the answer is they all are, really, just in their own way. They're just describing the same reality at different levels of detail. The best way to think about it is like a set of those Russian nesting dolls. The Arrhenius theory is the smallest doll on the inside. It's very specific, only works for H+ and OH- in water. It fits perfectly inside the next doll, the Brønsted-Lowry theory, because a proton donor is just a special kind of an electron pair acceptor, right? And both of those fit inside the biggest, all-encompassing doll, the Lewis theory of electron pair exchange. So let's just recap it real quick. Arrhenius was focused on specific ions in water. Brønsted-Lowry zoomed out to the action itself, the transfer of a proton, which works anywhere. And then Lewis gave us the most fundamental view of all. It's all about the movement of electron pairs, which covers reactions even when there aren't any protons around. So which theory do chemists actually use day to day? Well, as one chemist put it, it's all about using the right tool for the job. I mean, you don't need a supercomputer to do basic addition, right? You use the model that best and most simply explains the situation you're looking at. So for most everyday acid-base reactions that happen in water, like the stuff in biology or environmental science, the Brønsted-Lowry proton transfer model is perfect. It gets the job done. But for chemists who are designing new molecules, or working with metals, or deep in organic chemistry, the Lewis theory of electron donation and acceptance is absolutely essential. And that leaves us with a final and pretty fascinating thought. The Lewis theory is so incredibly broad that it basically reframes huge areas of chemistry. Reactions you would never have thought of as having anything to do with acids and bases, like how metals bond to molecules, are suddenly seen in a totally new light. It really makes you wonder, what other chemical reactions are out there, hiding in plain sight, just waiting for the right definition to make everything click?